Hello everyone. In this video we will continue to examine topic 12.1, the interaction of matter with radiation, and in particular we will continue to consider the photoelectric effect. So in the previous two videos, the experimental apparatus designed to investigate the photoelectric effect was introduced. And in particular, we described how one might measure the stopping voltage as well as sort of the maximum current reached when the applied potential difference was positive. So as it turns out, there are four very surprising results that stemmed from this particular experiment, and I will go through them in order and simply describe what the result is. Moving forward, we'll describe sort of why they were surprising and what one might have expected, but in this particular video, I'm just going to describe what those results were. So, as it turns out, the intensity of the incident light does not affect the maximum kinetic energy of the electrons, but it does affect the maximum photocurrent. So, remember that we're measuring the maximum kinetic energy with the stopping voltage. And so as it turns out, if you crank up the intensity of the incident light, you do not affect the maximum kinetic energy of these electrons. And naively, that's a little bit strange. We will talk about why in a bit. But, I can crank this up as much as I want, turn this dial to maximum power, and the maximum kinetic energy of the electrons released will not be affected at all. The maximum photocurrent detected is affected, is affected. That is, it's going to raise the ceiling here, but it's not going to raise or increase the stopping voltage. What else happens? The second surprising result is that the maximum kinetic energy, measured with the stopping voltage, does depend on the frequency of the incoming light. So if you go from infrared to optical to UV, you see an increase in the maximum kinetic energy as measured with the stopping voltage. You see an increase of the maximum kinetic energy as measured by the stopping voltage. As the frequency of the light increases, the maximum kinetic energy also increases. Third, below a frequency known as the threshold frequency, there are no photoelectrons emitted at all ever, no matter how intense the light. So if, for example, below the threshold frequency, which maybe is in the optical, if I shine infrared light at a particular metal and I'm getting no electrons, then I can crank the intensity up all I want, and no more electrons are ever going to be emitted. And that's a very strange result. I'm making this light brighter and brighter and brighter. The intensity is going up and up and up, and no electrons are emitted. And then finally, the fourth and final observation is that the photoelectrons, as measured by the photocurrent, are emitted with zero time delay. So at low intensity light here, you might expect there to be a significant time delay between when you turned on the light and the electrons finally had enough energy to be emitted and then be absorbed here. But as it turns out, there is zero time delay in all of these cases. And it's important to recognize that all four of these results can be explained, but all four of them are surprising on the wave theory that will be discussed in the next video.